PARSEC has been developed by a team of Northeastern University students as part of NASA's Moon to Mars Ice and Prospecting Challenge. PARSEC is capable of autonomously excavating, melting, and filtering Martian subsurface ice while simultaneously providing geological insight. Welcome to PARSEC.
At PARSEC's core is an NVIDIA Jetson computer capable of running automation and control code, as well as complex digital core data models. To control PARSEC's hardware, the Jetson communicates to various custom microcontrollers via USB and RASC serial. This allows the Jetson to set higher-level commands to control actuators, while bare metal microcontrollers handle the time-sensitive work of actually actuating them. To control PARSEC, an operator can use a ground station laptop connected to the Jetson with an Ethernet cable. The ground station then automatically connects to the Jetson's RAW server, and our custom UI can be booted up. This graphical user interface allows almost any operator to move PARSEC and observe sensor data in real time, along with viewing multiple accompanying video streams.
PARSEC uses a rotary percussive masonry auger drilling system guided by a pair of linear rails. It is positioned using a ball screw and nut. All the load on the drill is transferred through this load cell for use in competition and digital core. An upper dampener reduces vibrations and a lower stabilizer prevents the auger from wobbling. PARSEC is supported by a lumper frame during testing. It uses swappable sample cores and a bucket to simulate the Martian layers and subsurface ice. Here you can see PARSEC drilling through a sample tube composed of layers of concrete, clay, sand, stone, and ice. PARSEC is capable of drilling through a half meter of simulated regolith in just 16 minutes.
PARSEC's 3-tool carousel swiftly rotates up to 360 degrees in order to access new holes and swap tools. It is precisely driven by a 100-to-1 planetary geared DC motor with an integrated encoder. Its rotation can be locked by 2 linear actuators which nest into 24 holes at the base.
Ice is melted and extracted using a second tool, which contains a pair of 400-watt cartridge heaters. The melting tool can rotate and articulate, which results in a large hemispherical melt cavity. Water is then extracted through a stationary tube and sent to the filtration system. Several melting tests have been performed, revealing successful temperature control and a 3.5 liter per hour melt rate.
Filtration consists of a 2-layer mesh filter optimized for removing sediment and particles above 1 micron. Its second stage utilizes an RO membrane which removes the remaining impurities, yielding potable water. Water mixed with sand, potting soil, and clay was successfully filtered, resulting in safely drinkable water.
PARSEC's digital core uses a suite of machine learning algorithms to provide real-time guesses for materials being drilled through, in addition to a more comprehensive final prediction of layer identity, position, and hardness. The classification models used for these tasks have been trained using a variety of data from drilling including current, weight on bit, and other sensor data, as well as audio data from contact microphones. The different machine learning models were tested using data from following drilling tests and found to be successful in determining regolith layers. Specifically, the neural networks were found to outperform all the other models.
PARSEC's core analysis tool takes advantage of the unique opportunity to access exposed Martian subsurface layers to collect samples for research purposes. It uses a rotary tool to scrape away layers of regolith, directing them into a rotating sample holder. Thank you for watching PARSEC's integration video, and a special shout out to the entire team of student engineers who contributed so much to this project.